Alright, video number 3 for Garman Kohlhagen. This one's going to be about solving these two SDEs because the solutions we'll need in the next video to solve the PDE. This should hopefully be a pretty short video. I just didn't want to have to do it in the middle of the solution and have that be a super long video. So I'll just do it here as a separate video, and hopefully it goes a little smoother than the last video. I got a little sloppy and made some mistakes, but I think I figured them all out, luckily, as I went along. The main one was just, I'll reiterate again, I was talking about, I think when we were doing one of the Ito quotients, it was either this one or the other way. I was mixing up which one was X and which one was Y, and I talked about how foiling something would drop it out, which is totally untrue. But anyways, all the derivations were totally correct, so no worry there. And I did eventually catch it and explain it. So I think it comes right in at like the 4-minute 30 mark of 4 minutes and 30 seconds in the last video. I say something wrong, but I fortunately don't calculate or drive anything wrong. So anyways, let's move on with this. So we'll do the QD, or we'll solve this QD SDE first, and then we'll do the QF. What I mean by solve is, you know, we have now these in terms of the differential at time little t, so what we want to do is solve for x. I'll keep it as, we want to solve for x at time big T. So let's start again with the QD solution. So what we're going to do, so this will all be, you know, the same logic as a solution to geometric Brownian motion, which I also did in the third part of the Black-Scholes series. So what we're going to do is consider the function, the log, I'll just write log, whatever, I mean ln's fine. It's just log of x. Okay, so we're going to apply Ito's lemma to that, so we'll get that equals, of course, there's no time derivative because this doesn't depend on t, so you'll just have 1 over x dx minus 1 over x squared dx squared. Alright, so let's, you know, for our case, let's fill these in. Sorry, that's not totally, it's not right that like that. It is df, but let's just from the get-go start writing that. Alright, so we obviously we have this and this, so we'll have that d log of x is equal to 1 over x. And again, we're doing this for the QD dynamics. So we have RD minus RF x dt plus sigma x dWQD. So obviously quickly we see that the x's cancel. And then we'll have minus 1 over x squared. And for this term, again, you can prove this to yourself, but thinking about the Ito multiplication rules, so we're going to have this squared. So all that's going to remain is the dw term squared. It'll become dt, and so you'll just get sigma squared x squared dt. So obviously, again, these cancel. Sorry, there's a 2 here. It's 1/2. Okay, so when we simplify and bring together like terms, we're going to get that d log of x is equal to, we'll have rd minus rf minus 1/2 sigma squared dt plus sigma d wq dt. So we're going to integrate. That's strange. That is really, really strange. Okay. Anyways, so we're going to integrate this with respect to t. So we'll have that log c that, I could have had the dependence here, but I didn't, whatever. Minus, and then we're going to have the, of course, the initial condition, but here we're thinking of, between time little t and time big T. So little t is right now. It's not like this is some kind of, forward start process. It's just we are at little t. Just using that convention instead of time 0, but it would all work out the same way. So we have that is going to be equal to t of rd minus rf minus 1/2 sigma squared. Or sorry, I'm getting ahead of myself. dt plus t to t sigma dw q d. Alright, so these are pretty straightforward integrals. We're just going to have log x t minus log x at little t is going to be equal to rd minus rf sigma squared t minus t, and then plus sigma w q d. And I'm going to do this by just doing a subscript big T minus little t. Okay, so what we want to do now is we can move this to the other side. So we'll have that log x at big T is equal to log x at little t plus rd minus rf minus 1/2 sigma squared t minus t plus sigma wq d t minus t. Alright, so now we're going to exponentiate both sides. So here, so obviously when you exponentiate a log, those are just going to cancel. Actually, no, that might confuse you. Let's do it like this first. So we're going to have log equals exponential Alright, now recall that basically if you have something like, exponential of x plus y, you can just rewrite that as exponential x times exponential y. So in that regard, we can rewrite this big T as equal to exponential of log x at little t times exponential of that, because we have this plus here, so it's the same type of idea. Rd minus Rf minus 1/2 sigma squared t minus t plus sigma wqd minus t. Okay, and now again, exponential of a log just cancels. Okay. Sorry. I can't seem to do one of these without some little brain fart. I exponentiated both sides, so we're of course not dealing with log xt on that side anymore. It's just x big T. Alright. So anyways, the exponential and the log cancel, so you just get, the xt just comes down. So finally, you have that xt is equal to the initial value. Again, we're considering initial time as little t, so that initial value times the exponential of rd minus rf minus 1/2 sigma. Clean that up a little bit. Sigma squared t minus t plus sigma wqd. All right. And if you're familiar with, the solution to, say, a geometric Brownian motion for an underlying stock, that should look very, very familiar. So this is the, again, solution to the QD SDE. Now, again, we also want to find the solution to the QF SDE. Now, again, I'll write it here just so you don't have to go back. It was Rd minus Rf plus sigma squared xtd t plus sigma xt dwqft. Alright, so same idea, we want to solve this. Now, if you're familiar with this, or maybe saw the third part of my last series, or simply, are good with seeing patterns and analogies, you can probably see that, okay, basically we have this added little term plus sigma squared in here, so it's probably just going to happen that this is going to become a plus 1/2 sigma squared, right? Well, yes, that's exactly what's going to happen, but just for the sake of being thorough, let's actually go through that. So again, we're going to consider log of x. So again, we're going to have that differential of log of x. So we apply etos again. Etos lemma to this function, so d log of x is going to be equal to 1 over x dx minus 1/2 x squared, or 1 over 2x squared, I should say, dx squared. Okay, again, we have dx, so let's go ahead and fill that in. Log x equals 1 over x, and then we're going to have rd minus rf plus sigma squared x dt plus sigma x dwqf at t. Alright, so we see that again, the x's cancel, and then we're going to have minus 1 over 2x squared, and again, I'm not going to go through all the algebra, but again, we're just going to have this term, the dw term squared again, so same as last time, we'll just have sigma squared x squared dt. So again, these cancel. So simplifying and bringing together our like terms, we have d log of x is equal to, we have rd minus rf plus sigma squared minus 1/2 sigma squared dt plus sigma dwqf t. So again, like I said, these two then simplify to have plus 1/2 sigma squared dt plus sigma dwqf t. So again, we're going to integrate with respect to t, and remember we are between time little t and time big T, so we have log x at time big T minus our initial x little t equals the integral from t to t of rd minus rf plus 1/2 sigma squared dt plus the integral t to t sigma dwqf. Alright, so again, these are very straightforward integrals, and I'll go ahead and also at the same time move this term over, so we'll have log xt equals log x little t plus rd minus rf plus 1/2 sigma squared t minus t plus sigma wq. And again, for this, I'm just going to use like a subscript of big T minus little t. So again, we'll exponentiate both sides and then use that same idea that, you know, this is equal to that, and also that, say, that is simply equal to that. That'll get us our initial condition back. So again, in the end, we'll be left that x at time t is equal to our initial condition at little t times the exponential rd minus rf, and this time plus 1/2 sigma squared. So that's the only thing, again, that differs from the previous solution, and then plus sigma wq f t minus t. Alright, so that is the QF SDE solution. And just to have it here, let me write the other one. It's just r, d minus rf minus 1/2 sigma squared t minus t plus sigma wqd. That was the, again, the QDSD solution. So the only real difference, again, is these terms. Okay, so those are the solution to those two SDEs that we'll use in the next video to solve the PDE with Feynman Kac. Now, if you're familiar with Black-Scholes or even saw my last set of videos, you know, this is directly analogous to when we figured out the solutions to the Q SDE for the stock price, and also the QS SDE for the stock price. So for the Q SDE, you know, you basically had, so for this part here, you had r minus 1/2 sigma squared, and then for QS, you had r plus 1/2 sigma squared. And so that's where those differences between D1 and D2 come from in the eventual solution, if you're familiar with the Black-Scholes solution. And, maybe you always wondered why, why does D1 have, plus 1/2 sigma squared, but D2 has minus 1/2 sigma squared? It's because of the fact that due to the conditionality of the first part of the equation, you need to change measure from Q to QS. So same idea here, and since Garman Kohlhagen can just be seen as a modified Black-Scholes, you're dealing with the fact that you have differing interest rates between the domestic and foreign bank accounts. It seems like it worked out as it should, that we have very, very similar analogous solutions to the two SDEs. Alright, so with that, I'll stop this video. And next video, we'll finally get to deriving the solution to the Garman Kohlhagen model. So the pricing formula for a foreign exchange option under this model. And we'll do that via the Feynman Kac formula.